Okay, we said a lot of what you saw on the previous video in class. Let's just, if you need to review the example that we had in class, here it is. Now we did start with this upside down graph of omega of t, and if you were in class you understand why that had to be upside down. It has to do with glare on the screen and limitations of zoom. So we'll talk about this in a minute, but I'm going to focus here for a minute because you have the perspective of the earlier videos now. So here's theta of t, total rotations versus time, well, total rotations versus time t in minutes. Theta standing for the total rotations. Here's the graph. Between any 2 points, we can do a run and a rise. Now I actually drew this as if it was between 2 data points, and we generally won't do that. We generally smooth out uncertainties in our data by sketching a curve that as best we can represents, looking for an Euler-R word, represents the actual behavior of the system as opposed to the behavior it would have if we took our slightly uncertain results and took them literally. Okay, the curve smooths out uncertainties in our data. So here's the curve, and in this case I drew a tangent line at the 1 minute mark. Now we did an example on the original triangle, the rise and run, and let's say that you estimate or you have a rise of 8 rotations, taking the data literally, which we don't really do, but for an example, the rise between here and here would have been 8 rotations. This is on the data that I gave you at the beginning of class, the sample data that's not very realistic. Okay, so you got a rise of 8 rotations and a run of 40 seconds between these 2 points. The slope is 8 rotations over 40 seconds, which is 0.2 rotations per second. And 0.2 is a better way to write it, but we've got space and limitations here. So we got 2/10 of a rotation per second. Now rotation is 360 degrees. 2/10 of that is a fifth of that, which is still a pretty significant amount of rotation. You think about what these things mean in terms of the system that you're very familiar with for having spent a lot of time observing it. Okay, so there's an example of calculating a slope. Slope runs between the points 1 minute, I think it was 1 minute 12 rotations and 2 minutes 20 rotations. Okay. There it is. Now, we can do a tangent line. And using the tangent line at this point, of course we get the tangent line with a straight edge. Line it up so that it doesn't cut the curve. It just kisses the curve at this one point. And then, incidentally, if you haven't known what a tangent line is since the time you took geometry, there's a shortcoming in our teaching of geometry, which I fear is really, really pretty egregious. That's just a side comment. Okay. To estimate the slope of the tangent line, we estimate 2 points in the tangent line. So we actually estimated them. We said, okay, here where it intercepts the x-axis, it's at negative 24, 0. Over here, it's at 120, 27, 120 seconds, 27 rotations. Now that's the tangent line. That's not what the actual rotation. We're not going to get 27 rotations in 120 seconds. We got 20 rotations in 120 seconds. So these points don't have anything to do with the actual behavior of the system except that they're an auxiliary calculation that gives an auxiliary calculation for the slope of the tangent line. So now we can, if we wish, if we don't do this, we should at least visualize it. right here is a fundamental triangle that allows us to predict the actual angular velocity at this point. Well, we do that. We take the rise divided by the run. It's very clear that the run from negative 24 to 120 seconds is 144 seconds. That the rise is from 0 all the way up to 27 rotations, 27 R standing for rotation, again, space limitations, and having to write big so that zoom would make it. So the limitations of zoom resolution, or maybe it's not zoom, maybe it's the camera on this really pretty very good laptop. Okay, not the highest end laptop, but it's a relatively high end laptop. But they didn't put a really great camera in it. And since it's colleges, I can't install anything on it. I got to get somebody up there to install, and with COVID and the fact that they're hustling like crazy doing other things, we haven't been able to get that to happen. Hopefully we'll. Okay, anyhow, we got the rise, we got the run, we got the slope. And we calculate the slope in the obvious way. Now, slope here we get is 0.18 radians per, rotations per second. And it compares pretty well with the 0.2 rotations per second. And that's going to compare fairly well with the omega that you get in this upside down graph. Over here, now I've got a small representation of omega of t. The graph of omega of t has some curvature to it. And it's a kind of curvature that's pretty well modeled by a quadratic function, meaning that omega of t is going to be approximately, have the form at squared plus bt plus c. Now another thing, we can put a straight line through these data points, and the straight line does a pretty good job. It comes pretty close to our data points, comes pretty close to the curve that our data points do seem to indicate, and we've got to maybe try to figure out, there's where some experimental physics comes in, we've got to try to figure out why this thing isn't linear, why it deviates from linear, why the omega of t is actually a bit curved. Could have to do with air resistance, but I doubt it. Could have to do with friction not being as linear as we always assume it is. Something to delve into as we go through the course. Anyhow, we have our omega of t, straight line. It's going to have an mt plus b equation. We can easily figure out this equation. We can easily figure out this equation if we remember a little pre-calculus and can do a couple of simultaneous equations. We'll worry about that a little bit later. I introduce the symbol alpha, and I did this to clarify the notation that you saw in the document that we worked through. I didn't have time to run the document through an HTML to convert the HTML in which I wrote the original document to something that looks like this. So I had to write this for omega, and ampersand omega semicolon, that's an omega. Ampersand alpha semicolon is an alpha. So in answering the questions that I posed, we have that. Okay? So, here I talked about the conversion between rotations per second and degrees per second, because this omega versus t graph is in degrees per second, and our results here are in rotations per second. Well, it's a very easy conversion of units, and as second-year engineering students, you're going to understand how to do the units, and you've got your algorithm for doing them. I've got a little bit of a shortcut to that, but either way you do the conversion is fine as long as you do it right. Okay, so 0.18 rotations per second equals how many degrees per second? Well, a rotation is 360 degrees. So if I replace a rotation here with its degree equivalent, 360 degrees, and then do a little multiplication, I get what you get if you do the whole thing with lining up your units and canceling stuff. But you're going to get the same thing either way. So any way you do your conversion is really okay with me. I kind of recommend that you understand this because it can shorten things and save you a little bit of your lifetime. But you don't want to go to too many. You don't want to push it too far. You get yourself confused. There's a point to doing it the way you've been taught to do it. There's a point to being able to do it this way too. It can be a time saver. Okay. Well, anyhow, I say here, the slope here is omega average for the interval from 60 to 120 seconds. We talked about that in the previous video. I don't have anything to add to that. And then you have this big deal that, and big deals really need to be highlighted. So I highlight it by putting a big red circle around it, and a couple of asterisks around it, and a couple of stars, and whatever. Okay? Big deal. The limiting value of delta theta over delta t as t approaches 0 is just the derivative d theta dt. Now, what's that mean? Well, one thing it means is if we've got omega of t equals at squared plus bt plus c, we can take the derivative of that function and get our alpha of t, okay? And that has an interpretation that we'll be talking about. Very important, key, critical, essential thing. Aristotle got it wrong, Galileo fixed it. Or if we have, okay, well, I just talked about rate of the d omega dt. Okay, d omega dt gives us our alpha, okay, derivative of omega. And should be fairly close to this slope of this graph, and don't worry about that, that's kind of a digression. We'll get specific about it. Okay, if we had a formula for our theta of t, we could calculate its derivative and compare with what we get for our omega of t in this form or in this form, more accurately in this form, with a reasonable degree of accuracy in this form. So that's what we're really up to. Now I'm going to turn this thing over, see if there's anything I need to say about what we see on this side. A little comment here on what you get if you do a slope of this graph. Slope of a fundamental triangle in this graph, your rise is going to be a change in omega in degrees per second. Your run is going to be a time interval in seconds. So you're going to divide rise by run, you're going to be dividing degrees per second by seconds. And what does that mean? Well, first of all, the units degrees per second divided by seconds, just by the rules for fractions, is degrees per second times the reciprocal of seconds, which is degrees per second squared. But it's also, and we commented on this, somebody gave an answer in this form. It's degrees per second. Or if you want, degrees per second. It's how many degrees per second your omega changes every second. A meaning that you really want to ponder because it's not intuitively obvious. Okay. Let's see, I think that's all. I started to walk toward the camera. And we, of course, did a slope based on these 2 points. If you complete the triangle here, where'd that chalk go? if you complete this triangle, you got a rise. And if we're going in this direction. Negative 70 degrees per second. A run going from this point to this point in this direction of 400 seconds. And here we calculate the rise over the run to calculate this approximate slope, which would be negative 0.175. When we did this, I said the question is, what are the units? Okay, well, the units are degrees over seconds, degrees per second over seconds, as we said.